Question 5 of the practice final exam for today. I'll be working through question 5 from the practice final exam for Physics 457 for the upcoming final exam. Question 5 reads, a piece of wire has a uniform resistivity ρ, circular cross-section A, and length L. Nichrom's resistivity is a constant over a very wide range, and we'll call that constant ρ. The right end of this wire is held at constant electric potential V is equal to negative V naught, and the left end is held at V is equal to V naught. We take the Z hat direction to point to the right, the S hat direction points outward from the center of the wire, and phi hat determined is normal way via the right hand rule, which will be curling around the wire. Question A asks, in terms of the parameters given, what is the current density in the wire? So we want to know what the current density is. So we're looking for, in part A, we're looking for J. That's current density. Okay, and this has resistivity ρ. Now, if we recall, we want to know what is the current density. And the formula that we know for current density is based off of Ohm's law. And that is that E is equal to ρ times J. So we have the electric field is equal to the resistivity ρ multiplied by a current density J. So, of course, if we want to solve for J, we can just say that it's equal to E over ρ. So if we can find E, we can find J. E is easy enough to find for this wire, given that E is in one dimension for uniform resistivity is just given by the change in potential over a certain distance, which in this case we'll call the length of the wire L. So we have the change in our potential, which goes from, it's the negative change in potential over our distance L is what's given by E, because we know that E is equal to the negative integral of V dot dL. So we have that this is given by negative, and we have negative V naught minus V naught over L, given that our length of our wire is L, and our change in potential from negative to positive is negative V naught minus V naught, which gives us an overall 2 times V naught over L. And this is, of course, in the Z hat direction, as we are moving along the wire in Z hat. So the change in potential is in the Z hat direction. We have a total change of 2 times V naught over a certain length L. So our electric field is given by 2 V naught over L Z hat. So our current density J is simply given by E 2 V naught over L multiplied by our uniform resistivity ρ, and that's in the Z hat direction. So for this question, part A, when it asks us to find the current density of the wire, we know that the current density will be moving in the direction from positive V naught to negative V naught in the Z hat direction. The uniform resistivity ρ of this wire is what we can use when we look at Ohm's law, and we can relate the electric field to the current density J, because we can find the electric field simply due to the fact that this is just a nice uniform straight wire with a potential difference across the two ends. We know that the electric field is essentially the negative of that potential difference divided by the length of the distance between the difference and the endpoints, and we can figure that out to be 2 V naught Z hat over L in the Z hat direction, and then we simply solve for J. Now we will solve part B and part C of question 5. Part B asks, this figure has the wires reproduced here with slightly larger dimensions. On the figure, draw the electric field lines to describe the electric field inside the dashed box. So I'll draw this dashed box where we want to express the electric field lines inside of this box. And it says that the center of the box, the center of this line, is where the potential is equal to 0. And if E is equal to 0 anywhere, label it in the picture. So in part A, we calculated that we have our electric field is equal to 2 V naught over L Z hat inside of that wire. So we know that it's going to be pointing in the Z hat direction inside of this wire. And because it's a uniform wire, the potential difference is on both ends, we know that the electric field inside of this wire will be the same everywhere. So these electric field lines should all be the same. Now, as soon as we go outside the wire, we'll start to have our fringe fields, where we have it comes off, goes horizontal, and then comes back down. That's kind of what the fringe field looks like outside of our wire, as the electric field kind of has these eddies off of the edges. So again, we have that our electric field is constant in the positive z-hat direction with this magnitude at all points inside of the wire. And then on the outside, we'll start to have these kind of curving, smaller electric field components that are kind of the fringe fields coming off of that wire. So those are the directions inside of that dash box. And then part C asks us to say, to find a relation between all the electric fields at these different points. So it says there are a number of different points in the figure where one could look at the magnitude of the electric field. So point B and point F are the same distance from the left and the right ends of the wire respectively. Point A is directly above point B, and it's 1/5 of the wire's radius away from the surface of the wire. Points C, D, and E are in a line in a plane that bisects the wire. Points C and D are inside the wire, and point E is a 2-wire radius away from the surface of the wire. So in the diagram on your exam, it's below the wire, but here, because it's symmetric all the way around the wire, I've just drawn it above because I don't have space below. So point E essentially contains the same information, even though I've drawn it here above the wire, and on your exam it's below. We want to rank the magnitudes of each of these electric fields at each of these different locations based off of their location and their size, and if any of them have the same size, we want to state that explicitly. So right away, like I said in part B, and what we calculated in part A, we know that any electric field inside of the wire has the same magnitude. So right away we can say that EB equals EC equals ED equals EF. So the magnitudes of all 4 of these electric fields are at each of these points are equal, and that's because they're all within that wire. So they all have the same magnitude. And of course, as we move away from the wire, that electric field present in the fringe fields will decrease in magnitude. So eventually as you go to infinity, as you're infinitely far away, the electric field will go to 0. So we know that these are all greater than the electric field at point E. So now the outlier point is point A. And I will admit, when I initially did this problem, I figured that point A would also be smaller in magnitude than EB, EC, ED, and EF, because again, it's part of the fringe field, it's outside of the wire, does not have the same magnitude as that inside the wire, therefore it has a smaller magnitude, and because it's outside, it will be greater than EE because it's closer, but it will still be smaller than these ones. However, what we'll see is that because of how close it is to the wire, even though it's outside, the electric field vector at this point will be pointing in that direction, kind of like what we see with the fringe fields here. It comes off the wire, will go across horizontally, and then go back into the wire. What that means is that this electric field vector will have X and Y components. So, Z-hat component, and then an S-hat component away from the wire. And what that means is that it will not only have a component in the z-hat direction, and even though that z-hat component is smaller because it's a fringe field, it will additionally have this component in the second axis. So what that means is that the magnitude will be based off the hypotenuse of this electric field line, and it will actually be larger. So we say that EA actually has a larger magnitude than the other 4 of the other 5 points. So again, just to kind of recap how we looked at this problem, any point within the wire has the same electric field, since that electric field is constant within that wire based off the potential difference of the 2 ends. So we can equate these 4 magnitudes simply saying EB, EC, ED, and EF all have the same magnitude. Of course, EE is way off in our fringe field, so it will have a smaller magnitude. As we go away further in distance, the electric field drops off in size. And EA, which again I thought would have been smaller to begin with, but after kind of thinking about it and looking at this problem, you can see that because it has not a horizontal component, but it has a horizontal and a vertical component off of this wire, we see that the magnitude will be along this hypotenuse, and the magnitude of this electric field vector will be in fact larger than the other 5. So that's how you can rank these electric fields. And I think I can answer part D quickly as well, given that we already have the answer right here. So this is the answer to part D. But part D asks us, what is the electric field ED in terms of the parameters given? So again, the electric field at any point within this wire will be the same. So EB, EC, ED, and EF will all have the same magnitude. And again, we calculated this electric field in part A, so I'll go through it quickly once more, where again we have that the electric field is equal to the negative change in potential over the length in the z hat direction, because the potential changes in the z hat direction. And of course we see that this is just negative V naught minus V naught over big L z hat. And we end up with the electric field, the D component, is 2 times V naught over L in the z hat direction. And again, at any one of these points inside of the wire, we will have this magnitude for the electric field. At any point within the wire, it will be that magnitude. And that concludes question 5 of the practice final.